solids. And this is the joint work with Alan and Rayleigh at Prof. So, very quickly, I'm going to talk about mechanics of residually stressed solids and examples, defects, and the relevance of geometry. Marcelo already talked about geometry, so very briefly, a couple of things. And how we see geometric elasticity and anelasticity, and material manifold. Then inclusions and ion strengths in nonlinear solids. Overwhelmingly, everything is linear, starting with the work of Eshelby that I'll be mentioning. So you will see a very explicit example of a Riemannian material manifold here. So the goal is to calculate the stress field of an inclusion. So I will look at two examples: spherical inclusion and incompressible ball, and also a special class of compressible materials, and then I'll end with conclusions in future lectures. So, but anytime you talk about residual stresses, we should mention defects. So, dislocations were classified by Volterra, a great Italian mathematician. So he talked about dislocations at least 20 or 30 years before anyone was able to see them experimentally. So he called them distortions, and what we call dislocations were called dislocations by Love, a mathematician in the UK. So let me just quickly mention these things about defects. So the overwhelming kinematic assumption is this FEFP decomposition that a lot of people don't like. Goes back to Bilby, Kroner, Lee, and maybe other people. Geometric methods and the relevance to mechanics of defects goes back to the 50s, the work of Kondo, Bilby, and Knoll and Wang, as Marcelo mentioned. These are all very nice, but you don't see any residual stress calculations. Mostly kinematic discussions, very seminal, final. And there are some defect stress calculations for defects in the framework of nonlinear elasticity. Rosati's brothers at Caltech at the time. Zubov has a book that is pretty much ignored, and Amit Acharya has some interesting work. And let me also mention that there's some interesting history here. So Volterra looked at elasticity of non-simply connected bodies, and that was the beginning of dealing with defects. And at the same time, maybe 10 years earlier, his friend Poincaré started creating what is now called algebraic topology. But this connection was lost, and after maybe 150 years, no one really looked at compatibility equations, for example, for non-simply connected bodies. So this is something recently I looked at, but I thought that history was interesting. And okay, so these are a couple of examples of defects. So again, going back to the question of relevance of continuum mechanics, geometry and continuum mechanics, let me mention this quote from Kondo. So he pretty much says, it was remarkable that Riemannian geometry found applications in relativity, but at the same time it was unfortunate because when people see something finds applications in relativity, then the natural thing to think is, okay, this is something useful for relativity, no applications in reality. And it was strange to him that elasticity was not the first application, so it seemed more natural. And let me also mention that Cartman's idea of torsion is not the mechanical torsion. He was motivated by the work of Kazuma brothers, according to himself, in developing some geometric ideas. So there has been this.
Sorry, I simply want to comment to you that the situation maybe is even more complicated than this one, because luminifer ether technically is a Cossera continuum. I can give you the reference. So the story is even more complicated.
So just an example, so I don't have the whole story.
Yeah.
I would like to. And defects, I'm not going to talk about point defects, but you have line and point defects and surface defects. So the study of point defects goes back to Love at Oxford, and again, an issue will be continued. and you don't see any nonlinear solution. So my point here is people have done so many things in the framework of linear elasticity for obvious reasons, but it would be very interesting and natural to ask the question of what about nonlinear effects. So nonlinear elasticity is the real theory, and then you linearize if necessary. But unfortunately, in engineering, we start with linear elasticity, and for most of us, we just end. Okay. Marcelo already talked about differential geometry. So manifold, let me just say a couple of things. Something that locally looks like Rn. So these are examples of two manifolds. Locally, they look like something flat, but of course, globally, things could be very different. So here, you have examples of manifolds with boundary, and here you have the Mobius band, which is a manifold with boundary and non-oriented. And here you have an example of a two manifold that cannot be embedded in R3 without, you see some self-intersection. So in differential geometry, you look at manifolds intrinsically. So I don't need to have an embedding to understand a manifold, and that's the way I'm going to look at the so-called material manifold in the case of inclusions. And differential geometry is really a natural generalization of what we know in calculus and flat Euclidean spaces. And I'm not going to really use much of this, but a linear connection or a fine connection is what you need to move from one tangent space to the other. The parallel transport allows you to covariantly differentiate, and the metric is something that helps you measure distances locally. Given a connection and a metric, they don't have to be compatible. If they're compatible, it means this metric is covariantly constant. Given a connection, you have two important tensors. One is torsion tensor, which is the geometric analog of dislocation density tensor, and curvature tells you how far you are from being flat. And if you look at compatibility equations in nonlinear elasticity, they're written in terms of curvature tensor of some metric, which is the right Cauchy green strength. And just to look at these things in a more general form, so you're given a manifold here for us, a tree manifold, a connection and a metric. In general, they have nothing to do with each other. If there are certain conditions, this so-called metric affine manifold would have names. For example, what is a Riemannian manifold? It's a manifold with a connection and metric. There is compatibility here, there is no torsion, and of course this connection is the Lubitsch-Witta connection, but you could have more cases. And let me also mention Cartan, the father of modern differential geometry, and Weil, who pretty much introduced the idea of non-metricity, which is the covariant derivative of metric, and it's relevant in the study of point defects, but that's not what I'm going to talk about. So, nonlinear elasticity. So this is the classical picture. So this S and G is a Riemannian manifold. Let's say for us is Euclidean space, but it doesn't have to be. So this G is a background metric which allows you to measure distances. For example, if you're looking at motion of a membrane which is constrained to move in some curved space, then this background metric would be something non-flat. But let's say this is the Euclidean space. So you start with the reference configuration, which is, as I say, stress-free. If there are no residual stresses, and motion is a time-dependent map. And the problem is you may have sources of residual stresses here, and then people play a lot of different games. This FE, FP, FE, FG is one game. So now the idea is the following. I don't like FE, FP, and I start with this idea that reference configuration, in the reference configuration, the body is stress-free when there are no defects, no sources of residual stresses, right? Now, let's say there are sources of residual stresses, and depending on the source of residual stresses, now, eigenstrains I'm going to discuss explicitly, let's say I can find a manifold with some geometry in which the body, by construction, is stress-free. If I can find this manifold, then my problem is transformed to a classical nonlinear elasticity problem. Somewhere, a tree manifold, I can intrinsically define a map from a tree manifold to another tree manifold, and if I can construct this manifold, then I'm dealing with a classical nonlinear elasticity problem. And that's how I'm going to solve the inclusion problem. Okay, so if I'm doing all this, I need to kind of rewrite nonlinear elasticity, taking into account these two non-trivial geometries. Particularly this one is highly non-trivial, and I will show you concrete examples. So I'm not here I'm not just interested in beauty of the theory, but I like to be able to solve something, what we discussed last time. But beauty is, of course, nice. So, again, this G is a fixed metric, there has no dynamics. So here, this is not like relativity, so this G would have some dynamics. Fixed, even if you externally deform the ambient space, still there is no dynamics. But for us, it's fixed. So what people call deformation gradient is not really a gradient, it's just a derivative map. There is no metric dependence here. Material velocity, everything is static for me. The right Cauchy gradient strain is really the pullback of the ambient space metric. I'm going to be working with incompressible materials to simplify kinematics. So J or Jacobian tells you the relation between volume elements in the reference configuration and ambient space. And if you look at the classical formulations, they say J is determinant of F, but that you have to modify when you have non-trivial geometries in the reference and ambient space manifolds. And the other important thing is if you look at free energy or internal energy density, you're trying to make a scalar out of two-point tensor. So this, let's say, internal energy density explicitly depends on both metrics. Of course, you have your balance of linear momentum, and it's always easier to write it in the ambient space because your ambient space is flat in the examples. Okay. So you just need to write things very, very carefully. So let me just give you the maybe most trivial, maybe simplest, non-trivial material manifold. So if I give you an analyst and stress-free, uniformly increase or decrease temperature, and if this body is free to move, it would expand or contract without any residual stresses, right? Now, if I give it a change in temperature, which is axis symmetric, it would like to go to the third dimension like this to stay stress-free. If it cannot, it would have residual stresses, right? Now, let's say I have to stay in 2D, so this would have residual stresses. Now, this is how I define my material manifold, where I'm stress-free by construction. So why do you induce residual stresses? So your natural distances for these 2 points like this, after I change my temperature, becomes something like this. And because these natural distances vary from point to point, the rigid geometry of our two-dimensional Euclidean space cannot support that. But now let me imagine I put this body in the Riemannian manifold with a metric that explicitly depends on temperature the right way. Meaning that, so when I look at this underlying set here, the distance that I measure is really this, which is the natural distance that this temperature change is dictating. So in that Riemannian manifold, I'm stress-free by construction. So my problem is really now a classical nonlinear elasticity problem. In the case of thermal isotropic materials, you could explicitly write that and do some calculations, but just to give you an example. And before I move on to inclusions, so let me also mention this. So what is this material manifold where you're stress-free? It's very problem dependent. Given a set, you could give it many different geometries, and you could write very long papers that don't mean anything, so you have to really understand the physics. So just some examples. So, and Marcel already mentioned some of this. So in the case of dislocation, so the physical quantity is dislocation density tensor, torsion 2,4 or Berger's vector somehow, which is the areal density, is the relevant quantity. For disclinations, curvature. For point defects, non-metricity. For temperature changes, you could write down metric directly. Bulk growth, again metric. Surface growth, not very well understood as we discussed yesterday with Marcelo. And inclusions and inhomogeneities, and this is what I'm going to explain next. So when you have eigenstrains, you could directly write down the material metric. For defects, you have to do some more work to find that, but here.
So your idea is to introduce a metric in the reference configuration which is evolving.
Which is
Evolving.
If your residuals, yes, if you have this temperature, then you have the heat equation, and yes, it will evolve. But here for inclusion, I'm going to assume that there is this given eigenstrain distribution. What is this residual stress? Of course, if that evolves, this will evolve too. Okay. Okay. So very quickly, inclusion. So this goes back to Eshelby. So this paper Eshelby, the Proceedings of the Royal Society, as far as I know, is the most highly cited paper in solid mechanics, more than 6,000 citations, which is a lot for mechanics. So he looked at an ellipsoidal inclusion. So an inclusion with eigenstrain mean many different things. So he looked at this ellipsoidal inclusion in infinite solid, everything linear, isotropic, elastic, and he assumed that eigenstrain is uniform in the ellipsoid. And then what he proved was that stress inside the inclusion is also uniform. Very surprising result. So now my goal is to extend this to nonlinear elasticity. I can look at that in the generality that Eshelby proof. I don't think that result holds in general, but I'm going to be looking at a spherical inclusion with some eigenstrains that respect the spherical symmetry. And so there have been like some works to extend this to nonlinear elasticity, mostly for harmonic materials in 3D. There are recent results. This is what people call shrink and fit. So Antman has looked at this problem. And in 3D, the only existing result, as far as I know, is a numerical result by Dayani and Parks. And they look at some finite element solutions that they see, okay, yes, stress inside the inclusion is hydrostatic if eigenstrain is purely dilatation. So I'm going to prove this analytically for a ball with that inclusion. But so there hasn't been anything for 3D, and I'm not going to be restricting myself to harmonic materials, arbitrary isotropic, and then some class of compressible solids that include harmonic materials. So there's this back here. Okay, so let me also mention the monoforms. So now this is the problem. I have a finite ball with some eigenstrains which respect the spherical symmetry. Anything inside, and then if I can solve this problem, a spherical inclusion would be a special example. So if you look at your classical spherical coordinates, this is, if there are no eigenstrains, this is the flat metric. In spherical coordinates, that means ds looks like this, right? So if you don't have any inclusions, just use like the flat Euclidean space with this metric in spherical coordinates, right? Now, what I'm going to assume is that I'm given some eigenstrains which vary from distance from the center. I would have radial and circumferential eigenstrains that are not necessarily equal. And then at the end, if I have pure dilatation of eigenstrains, they're equal. But I'm able to solve the problem even when they're not equal. And now this is the metric. So instead of 1, you have some exponential just because it's positive. You could call it a function. So it's e to omega r. So omega r is some given function, and omega theta is another given function. Okay? And so this is my material manifold. So the underlying set is this ball, and then this is the metric. So given my eigenstrains in this Riemannian manifold and stress free. The problem is the moment I put this body in the Euclidean space, then I induce residual stresses. And that is what I'm going to calculate. See, this framework is so natural that such a hard problem you can solve. Because if
So your deformation energy will depend on this?
Yes. No, of course. And this, and then of course the motion. So you have this, and then when I say I put it in R3, it means like I'm looking at a map from this manifold to the Euclidean series. So now in the ambient space, or let's say if so this is my deformation map, I have little r, theta, and phi. Now this is the classical nonlinear elasticity problem. Because it's so symmetric, so first of all, this is the metric of the ambient space. Flat, and I'm going to use spherical coordinates again, of course. And I'm going to be looking for solutions of this form. R, theta, phi, R of R, theta, phi. Which means you only have radial displacements. Then this is the game that people play to solve some problems analytically. It's classic. So this is my material manifold. I'm looking at an embedding in R3. To simplify, first I'm going to assume incompressible materials. So that means J is 1, but you see I have to take into account all this. And you will get something like this, and assuming that R of 0 is, so this is the type of 0, to kill that rigid body translation. So I just get my kinematics. See, if omega R and omega theta are 0, R becomes big R. Of course, because there is no source of energy. And now, I'm not going to look at this particular constitutive equation like Newhookian and Mooney-Rivlin. I'm going to look at an arbitrary isotropic solid, but incompressible. So I need to calculate my stretches. There are different ways. One is to look at physical components of deformation gradient. So when you're, this is again classic. So when you work with curvilinear coordinates, a given physical quantity, like F or stress, you look at components, they may not have the right physical dimensions, and the physical components means like you change these components somehow to have the right physical dimensions. Something classic, and Truesdale has this nice paper in Montgomery. So, okay, these are your stretches. Eigenvalues of your stretch tensor, and C, eigenvalues of C would be these squared. Now, an isotropic material, energy function depends on your principal stretches, classical nonlinear elasticity. And if this is Newhookian, for example, it would be this one squared plus squared minus 3 times mu divided by 2. But I'm going to solve the problem for an arbitrary. And not just this, it could depend on R. If I have an inhomogeneous material, but again, spherically symmetric. So, depending on where I am, I have a different material, but isotropic. Then I can handle too. So, again, classic. So, the non-zero Cauchy stress components would look like this. So, dWd lambda 1 could be anything. So, it would be mu lambda 1 in the case of Newhookian solids. And pressure is unknown because of the internal constraint, of course, right? So the only unknown thing here is really pressure, because kinematics I have from incompressibility and everything else. Now, equilibrium. I'm going to write it in the ambient space because it's flat, easier. So this is the only non-trivial equilibrium equation, and I like to write everything referentially, or Lagrangian coordinates, right? Looks like this, and this will give you this very simple OD for the pressure. P prime is H, and this H depends on these two functions, omega R and theta, and everything else. So, for example, if this is Newhookian, this term will be 0. But now this is written for an arbitrary isotropic solid, but incompressible. Okay, so what are the boundary conditions? It could be stress traction free on the boundary, or pressure or tension. Again, this would still respect the spherical symmetry. So having that PR, calculate, and that H, I'm going to show you in a minute. And then the non-zero stress components would look like this after you have your pressure. Okay, so I'm actually going to show you. Okay, I did, so this is H. So now, given any omega R and theta, I have the solution. Now, to go and look at an analogy or a nonlinear extension of Eshelby's problem, I'm going to look at the following example. I have this big ball, and I don't have any eigenstrengths anywhere but in some smaller ball, centered at the same point. And let's say inside I have omega r is some constant omega 1, omega theta is some other constant omega 2. And then if they're equal, that means I have pure dilatational eigenstrengths. But I can solve the problem even if they're not equal. So, again, example, so kinematics looks like this. And first, inside the inclusion, these are stretches. And if you come back and look at your, so you see omega r and theta, particularly theta, this is a discontinuous function. There's a jump discontinuity. When I come here, you see you have this derivative of omega theta times something. So this is the derivative is a delta distribution, and this is like outside. There is an ambiguity in multiplying these two distributions. So there will be an unknown constant, so that your function h is some unknown a delta r minus ri, that's the boundary, plus h hat. So this a I need to calculate, and that I will calculate by enforcing continuity of traction vector on the boundary of your inclusion. Okay? And this h hat looks like, it's like you're simplifying that h and there is no omega prime term. Okay, so the first thing you see is that for r less than or equal to ri, h is some constant divided by r. And this constant looks like this. When omega 1 and 2 are equal, you could show that no matter what this isotropic solid is, h0 is 0. So h prime is 0, and you could show that your pressure inside the inclusion is constant. Okay, so remember I had these like integral terms for calculating pressure. So depending on where you are, you have something like this, and this h bar in these integrals looks like this. Again, a simplification of h hat. So this is the solution. Now your pressure field, this is what you apply on the boundary, is 0. You have this logarithmic singularity here, this unknown a, and outside the inclusion things look like this. Now the radial component of Cauchy stress would look like this. And then I don't know what this a is, but I'm gonna enforce continuity of traction on the boundary of the inclusion. That would give me this unknown a, which is now the last unknown. So inside the inclusion, radial stress is this form. So I have something that has a logarithmic singularity plus some sigma I constant, which looks like this. Now, if I have pure dilatational eigenstrength, this h0 is 0, you see the sigma r component is sigma I. And you could show that the physical component, so these are physical components of the other two, are also exactly equal to sigma I. Okay, so then we have this proposition that given an isotropic and incompressible elastic ball subjected to uniform pressure and its boundary, it could be 0. Suppose that there is a spherical inclusion at the center with uniform radial and circumferential eigenstrengths. Then, unless they're equal, there is a logarithmic singularity. If they're equal, stress in the inclusion is uniform and hydrostatic for an arbitrary isotropic but incompressible solid. Interesting, right? So, to see geometry gives you something highly non-trivial. You may expect that this result is okay, but this is the proof. Now, what about compressible? So I can do it for arbitrary compressible, but I'm going to look at a special class of compressible solids due to Carroll. So instead of saying W is a function of lambda 1, 2, 3, we could say, look, I'm going to look at the principal invariance of stretch tensor, which look like this. And if you do that, you would have this representation for stress tensor. So this is what Carroll wrote it when everything is Euclidean, so I simply extended that. It's just an easy exercise and geometric. And so in components it looks like this. So this is what we call a finger tensor, which is pushed forward of metric in the reference configuration. I mean, so you do things very carefully, but this is like really a simple exercise, extending that Cauchy stress representation. So this is now the special class of compressible solids that Carroll considered. So this W being a function of I1, 2, 3 said, I'm going to look at this special class with this additive property, that this function is some arbitrary function of I1 plus I2 plus I3. And then Cauchy stress representation would look like this. And so this is the special class that I'm going to be looking at. Now, for compressible, I'm going to assume that these two are equal. And I would have my principal stretches, I1, I2, I3. So my goal is to prove a proposition that we just did for this subset of compressible solids. In particular, what those two guys did numerically. Okay, so this V sharp inverse look like this. Cauchy stress has a representation like this, the only non-zero components. Now you look at equilibrium, it looks very similar to what Carroll wrote. Now I'm going to look at 3 examples, materials of type 1, 2, and 3 according to Carroll. So one is harmonic material, which means your V is linear in I2, linear in I3, but then the I1 dependence is an arbitrary function. And Carroll showed that it cannot be linear. If they're all linear, you would have zero shear modulus, or Poisson's ratio is -1. That's unacceptable. So when you take these two to be linear, the other one cannot be linear. And so you have this one governing differential equation, nonlinear, looks like this. Now, when I have pure dilatational eigenstrain, I would get this equation for both R less than Ri, larger than Ri, and then you could show that that means I1 is piecewise constant. You would get the kinematics. Inside, outside, so inside to make sure everything is bounded, you have C2 0, and then continuity of R will tell you that C4 is a function of C1 and C3 like this. So then your unknowns are C1 and C2. Then you have 2 constants, and those would be Cauchy stress being this. So what is this? This is Cauchy stress or traction given on the boundary, and then this is continuity of traction. And okay, depending on what this I1 function is, I could in principle solve this, and then assuming that I have those 2 constants, stress inside the inclusion, you could prove it's some constant. Those C1 and C3 are constants, so I can't like have it like as explicit as the other case, but I can prove it is still a constant. And then you have this proposition that you have a harmonic material, and you're respecting the spherical symmetry, pure dilatational eigenstrain in a ball, then Cauchy stress is uniform and hyperstatic. And so this, we showed it for like class 1 materials, for the other 2 holds as well. Okay, now, so I'm going to be half an hour, right? So I mean, I'll let you have your own concluding remarks, but so this reference configuration, so there has been some fights regarding this configuration of forces, reference configuration. I think I don't have a solution. I don't really care that much about configuration of forces, but I think one source of, one problem is this vagueness in defining what reference configuration is. When I look at Gerten's work, he talks about these evolving control volumes. What do they represent? It's not clear to me, please. And it's really a game. And so there's this fight with Mojan, and Mojan has a lot of good ideas, but material manifold, I think, hasn't been defined clearly. So here, it's where you're stress-free. There are some important unanswered questions. Is it unique? Can you have more than one? I don't know. I'm still solving specific examples, because you could just, talk about philosophy and beauty, all very, very nice, but before you solve a bunch of specific problems, you can't really say much, in my opinion. So I think this reference configuration plays a very important role when you have any source of residual stresses, and then if you have evolution of defects or these sources of residual stresses like growth, then you have this material manifold with an evolving geometry. And very recently, I mean the last 20 or 30 years, mathematicians have looked at Riemannian manifolds with evolving geometries. Probably the first significant work was by Hamilton. He introduced the so-called Ricci flow. So you have a Riemannian manifold, its metric is evolving depending on the Ricci flow, the Ricci curvature. And Perelman, this crazy Russian mathematician, used those ideas to solve Poincaré's conjecture. And so this is the guy who denied the field's metal. So this has been, people in geometry have looked at it. So for us, the analogy would be, so you have dislocations, external forces, these things evolve. So this reference configuration or stress-free configuration evolves. But for us, most likely, things will be much, much more complicated than just a simple Ricci flow. So probably you will have to do this. But this is an interesting direction. And you see, you can solve some problems analytically. It would be, I don't know if it's hopeless or, I can never say impossible, but this framework is so natural that certain problems you could solve really easy. Again, I can't say everything. So this is just one framework. In this framework, you can solve certain problems. And so problems more interesting with less symmetry. Can I do more work? I don't know. And for instance, like evolution of residual stresses. So I would say thermoelasticity would be the starting point because heat equation is very well understood. So we know what the dynamics is. Now coupling and trying to solve something would be very interesting, right? And so evolution of defects would be maybe the next step. Bulk and surface growth are very interesting problems, and maybe other things.
Okay,